Hello calculus students. Today we're going to talk about linearizations, which are sometimes also called the differentials section. So in this section our goal is to create a linear equation, which is specifically the tangent line to some function at a specific point. And we want to create this equation so we can use it in place of the original function. So when we create this linear equation, which is really our tangent line, they label it L of x and they call that the linearization. And then our original function will still stay with f of x notation, so you can keep those two straight. So just kind of looking at a preview example, suppose our original function is the square root of 1 plus x. And we say, well, find f of 2 without using a calculator. Well, f of 2 without a calculator would be the square root of 1 plus 2, which is the square root of 3, which, would be we just have to kind of guess. So, but suppose we create a tangent line to the function close to this x value of 2, which we call L of x. And when we do that, this is what the equation is going to be. And we're going to learn how to create this linearization equation. But that would be the linear equation, which is the equation of the tangent line at that point x equaling 2. So if we do this, it's going to input a value, an x value of 2 in it. It would be 5/4 plus 2/4, which is 7/4, which would be what? 1 3/4, which is about 1.75. Now that's not going to be exactly right, but hey, it's a good estimate. So let's just see how good an estimate it is. Now let's actually go to the calculator. Let's go to our f of x function and put the 2 into it, which is, legit, which is the true solution or the true value. And so that would be the square root of 3. And if we put that on the calculator, if you calculate the square root of 3, it's going to come out to be 1.73205. So you can see, hey, we didn't do too bad a job here of coming up with that value using a linear function. So what we're doing, kind of the overview here in this last statement, is saying, notice how similar that when f of x, the original function, notice how similar it is to this linear function that we create, which is really the equation of the tangent line at the x value of 2. So that's the goal. So we're going to take a look at some images here that show this point 1, 1 on this f of x graph, and right here, okay, and the tangent line to it. So the f of x is the blue line and the tangent line is the straight line, which is the red line. So your second image on the right here, they've zoomed in a little closer to kind of compare look at how the red tangent line is becoming more similar to the blue f of x. Then they do it again. Wow, this one, it's barely distinguishable between your tangent line and your f of x because they've zoomed in so tight. And last but not least, in the fourth graph here, they've zoomed in so tight that you really can't see any difference. And so that's kind of what we're doing here, is coming up with this tangent line so that we can use the tangent line, the linearization equation, to evaluate f of x. Alright, so let's come down here now, and here's another, take a look at this example. It says, linearization equations vary for the function according to the x value for which the tangent line is created. Okay, so what we're trying to talk about here is at this x value, this is where x is 0. Okay, so this would be the point, 0, 1. So your tangent line to the graph at 0, at an x value of 0, is extremely different than your tangent line to the graph at, say, this point, which looks like it's an x value of 3. Okay, so in other words, your tangent line as you move along the function, of course, changes. So your linearization, your linear function, is only going to give a valid result when you pick a value close to the point that you created the tangent line to the function. Alright, so how do we come up with this linearization equation, which is just an equation of a straight line? We had this old method, or this method called the point slope formula. Okay, this is the point slope formula. And this one, well, it's also a point slope formula. Let me see if I've got that right. What do we call that one? It's called the, that's right, this is called the slope intercept. I'm sorry, this is the slope intercept. Anyway, you don't have to kind of drag into these words, but anyway, these two forms of the linear equation. You can use either one of these to write your linear equation. It seems in the last year or two that most textbooks have gone with this slope intercept form, but this textbook is sticking with the point slope formula to write the equation of your linear line. So just a real quick review in applying the point slope formula. If we have this point slope formula and they want me to write an equation, and your equation is passing through the point 2, 5 with a slope of 4, then your 4, of course, is your m, your y1 is your 5, and your x1 is your -2. So when you're creating this equation, it's going to say y minus 5 equals what? 4x plus 8, and then when you add the 5, you come up with your equation of 4x plus 13. And this would be your L of x. Okay, your equation, your linear equation of your tangent line, which we call the linearization. Okay, so with that in mind, when you go to the textbook, they give you this big, wow, this is what L of x equals. You're like, where in the world did that come from? And then they show this diagram. Well, the first thing that you really need to note is, of course, your first derivative is your slope. So this is m. Okay, and f of a is your y value at the point. So here's our point of tangency right here. So this is the point we're using, and this is the slope we're using to write the equation of the line. So when we had y minus y1 equaling m times x minus x1, if I solve it for y by adding y1, adding y1 to each side of this equation, then you can see if you replace the f of a with y1 and the f prime of a with m, then you're back to this equation. So this is our point slope formula written with function notation. That's all it is. Okay, so remember, we're finding the equation of the straight red line, which we're naming L of x, which is the equation of the tangent line. Here it is written again from the book, the definition, where here's that linearization, and we're saying that this linearization is going to replace the actual function when we go back to that specific x value for which we created that linearization equation. All right, so this is really the first example that was in this notes back on page 1, and so I'm going to show you how to get that equation. I mean, we've used the equation, but now let's show how to get it. Of course, they do have to give me an x value because, again, the linearization equation, the equation of the tangent line, will vary for every x value as you get further from that point. So, okay, so we're going to go y minus y1 equals m times x minus x1, and we need a slope and we need the point. Well, the point, the x value of the point is 3. And so the point is on both our tangent line and on our function. So we can go back to the function itself to come up with the y value. So this y value is going to be the square root of 1 plus 3, which is the square root of 4, which is 2. So our point is 3, 2. Then we need to find the slope. Again, to write an equation, we need the point and a slope. So the slope is the first derivative of the function evaluated at the x value of 2. So my function is 1 plus x to the 1/2 power. So when I take the derivative, it's the chain rule, 1/2 in the front, then 1/2 minus 1. Then the derivative of what's in the parentheses, the derivative of 1 is 0, but the derivative of x is 1. So this becomes 1 over 2 times the square root of 1 plus x. So now, that's the derivative. That's my f of prime of x. So now I want to evaluate this at the given x value of 3. So this becomes 1 over 2 times the square root of 1 plus 3, which is 1 over 2 times 2, which is 1/4. So now, the two things I need are a point, and my point is 3, 2, and my slope is 1/4. So now applying this formula, This becomes y minus y1 equaling m times x minus x1, which is y minus 2 equaling 1/4 x minus 3/4. Then when I add the two, that would be adding 8/4, so this would become 5/4, which is my linearization, my L of x. Okay, we're renaming it L of x. Okay, so this is not f of x, this is L of x. This is my tangent line, my equation of my tangent line, which is called my linearization, up close to the x value of 3. So this is almost equal to my original function at that point. So we can use the L of x to evaluate the y value of the function given x values close to 3. All right, so there's your setup. So here's one more. If we do it at 0, we can go back, and we need a point to find my equation. To find my linearization, I need two things. I need a point, and I need my slope. Okay, this time my point is at an x value of 0. Okay, my point is at an x value of 0. So if I plug in 0 into this function, it's the square root of 1, which is 1. So the point is 0, 1. Now, to get the slope, I need to find the first derivative. Okay, so, we've already got the first derivative, okay, up above. So my first derivative, we found it above, to be 1 over 2 times the square root of 1 plus x. So my slope is computed. This is going to be the equation of my tangent line to the function at an x value of 0. So my slope of my tangent line at the x value of 0 is going to be 1/2. All right, so I'm ready to come over here and create the equation of the tangent line, which is referred to as my linearization function at the x value of 0, or in other words, at the point 0, 1. So this becomes y minus y1 equaling 1/2 times x minus 0, or just 1/2 x, or 1/2 x plus 1. So this is my linearization function. And if you go back to the earlier graph on the prior page, you'll see this equation as my linearization function at that point where x is 0, or the point 0, 1. And you also will see the 1/4 x plus 5/4 at the x value of 3 to go back up there and confirm those linearizations. Okay, here's another example. They want me again to find the linearization of the function. This time they're giving me a trig function. So this is the cosine function. It's my wave, which is my blue line. And it wants me to find the linearization of the function, which is the equation of the tangent line of the function, at the x value of pi halves. So again, to find my L of x, I just need two things. I need a point, and I need the slope. Okay, well the point is pi halves something, and then the slope is the slope of the tangent line at that point. Okay, so here's the point right here. It looks like it's pi halves 0, but I should not just guess from the graph. So if I want to take f of pi halves, this would be cosine of pi halves, and cosine of pi halves is a positive 1. Oh, cosine of pi halves, sorry about that. Cosine of pi halves is not 1. Cosine of pi halves is 0. So this is the point pi halves 0. That's the point of tangency, so this is the point pi halves 0 up here. Now I need to work with the derivative to find the slope at that point. So the first derivative is taking the derivative of cosine x, which is a negative sine of x. So now if I evaluate my first derivative at the x value of pi halves, it will be negative sine of pi halves. Well, sine of pi halves is 1, so this is a negative 1. So my slope, my first derivative is my slope. I'm going to scroll back up here. My slope is negative 1. Okay, so now let's find this function. So it's y minus y1 equaling negative 1 times x minus x1. So this becomes y equaling a negative x plus pi halves. That is your linearization function that you can use in place of cosine x, so long as your x value is really pretty darn close to pi halves. And so that makes it a lot easier to come up with those computations. Okay, here's another one. This is we're just doing a lot of algebraic practice here to kind of get a feel for this. Another, find the linearization of the function at the x value of 3 pi fourths. Okay, so to find my equation of my tangent line, which is called my linearization, I need to have my slope and I need to have a point. And the point is 3 pi fourths. Find the y value. Alright, so if my f of x is cotangent x, then to find that y value at the point 3 pi fourths, this is cotan of 3 pi fourths. Okay, so that's pi fourths in quadrant 2. So this is 1 over tangent of 3 pi fourths, which is pi fourths in quadrant 2, which is going to be a negative value for tangent in quadrant 2. So this is going to turn out to be 1 over the negative square root of 2 over 2, which equals negative 2 over the square root of 2, which normally we would rationalize that, but I've kind of noticed lately that the book is not rationalizing it. So I think I'm going to leave it like that for a little while. Let's just leave it alone and see how it works. So this point over here is negative 2 over the square root of 2. Sorry guys, my handwriting is not the best on this tablet. Okay, so now we need to find the slope. So to find the slope, we go to the first derivative. So I need to take the derivative of the cotangent function, and the derivative of cotangent is negative cosecant squared x. Cosecant x squared. Boy, it's not easy for me to write cosecant on this tablet. Okay, but that's cosecant. That's an S. Okay, so now I want to find this value, which is the slope of the tangent line at this point. It's going to be a negative, really, cosecant of 3 pi fourths squared. Okay, so cosecant, let's see if I got enough room here. Cosecant is 1 over sine of 3 pi fourths, which is a negative in front of 1 over, okay, sine at 3 pi fourths is square root of 2 over 2, and it's going to be positive in quadrant 2. So this becomes negative 2 over the square root of 2. So this is the slope of the tangent line, because remember, first derivative is my slope. So up here, my slope, oddly enough, is negative 2 over the square root of 2. Hold on, that's not what I have in my notes, so let me double check. Sine of 3 pi fourths is pi fourths in quadrant 2, which is square root of 2 over 2. Oh, and I've got to square it. Okay, I'm sorry, I forgot to square it. Okay, so I've got to square this. Square it. And square it. Okay, so this becomes 4 halves, which is 2. All right, make certain I get that correct, especially in this lovely recording. Okay, so now we're ready to actually come up with this equation. This is all my preparing for it. So now to actually write this equation using this information up here in the top right corner, I have y minus y1, which is a negative 2 over the square root of 2, equaling m times x minus x1, which is 3 pi fourths. Alright, so this becomes y plus 2 over the square root of 2 equaling 2x minus 3 pi halves when you distribute that 2. Then I just need to subtract that 2 over the square root of 2, which is, boy, it's hard for me to leave it like that, minus 3 pi halves minus 2 over the square root of 2. And that's about to drive me crazy to not rationalize that denominator. So I'm going to go ahead and write it now as 2 square root of 2 over 2, which is really just going to be minus square root of 2. There you go. There it is. There's my linearization. And don't try to put the 3 pi halves and the square root of 2 together. That is your L of x. Okay, that is your L of x. Okay, so now where does this go? Now it says, take a look at an example where we can evaluate a radical or square, a fifth root of a number.
Okay, so this is a question taken straight from my math lab. You can see I just used Clip It to kind of put it in here. Okay, so just kind of knowing what this question is saying, this is your f of x, okay? 1 plus x to the power k is your f of x. And the 1 plus kx is your linearization that they've already figured and they're giving to us. So they're saying, use your linearization function to approximate the value, oh my gosh, of 1.0002 to the 46th power. This is like question A. And then question B would be also the fifth root of 1.007. So there's two questions here. Okay, so let's take a look and we'll call it part A. It says, what in the world is 1.0002 to the power of 46? All right, so of course we're going to want to write this as f of x. Okay, so here we go. F of x is 1 plus x to the k power. So this could be rewritten, this question, I could write it as 1 plus 0.0002 to the fourth power. With that set up now, my x value is 0.0002 and my k is 4. So now I'm going to go to my linearization function. I don't have a lot of room here. I'm going to go to my linearization function, which they said is 1 plus kx. And I'm going to make this 1 plus 4 times x. Okay, so this is going to be 1 plus 0.008. So I get 1.0008. And that's what I'm saying should be approximately 1.0002 to the 46th power. So I don't know, let's just see how close we are. I'm on the calculator now, and I'm taking this number to the power of 46, and I'm coming up with, on the calculator, this is turning out to be, on the calculator, 1.009241522, blah, 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 blah. So, hey, that's not too bad. Okay, it's not too bad. We're really close to the 1/1000th position. We're close, very close, using our linearization. Now, I don't have enough room here, but if you wanted to try this second example, then what you would do is you would say, okay, well, f of x again is 1 plus x to the k. And so if I wrote this as 1 plus 0.007 to the 1/5 power, then I would have my x 0.007 and my k to be 1/5. So then you would plug it into your linearization function and make the comparison. Okay. All right, for sake of space, I'm going to keep moving. Also, I don't want this recording to be too long. Then we have these cool things called differentials. Again, remember the name of this section I think is actually called differentials, not linearizations. And so we're talking here, the differential is just dy. So this is pretty easy. Here's my given y. If I want to take the derivative, this would be 12x cubed minus 5. And then if I want to multiply both sides of this equation times, say, dx here and here, then these dx's would cancel and I would just have dy. So this would become, and you really should put this in parentheses, 12x cubed minus 5 dx. That's what your differential equals. So here's another one. Here's another example. A couple of examples here. If you're going to take the derivative, of course, we're going to want this to say 2x to the 1/2 power. So in this case, dy would be 28x cubed plus 1/2 times 2, which is 1, x to the 1/2 minus 1. And then out here, you would need to add dx. And so they would clean this up, and they would make it 28x cubed plus 1 over the square root of x dx, and that's what your differential equals. Here's another one. Here's my cosine. So if I wanted to find dy, okay, it would be 7 times the derivative of cosine is a negative sine. And so then it's a negative sine of 8x to the 5th cubed, and then you've got to take by the chain rule the derivative of the argument of the trig function. So this derivative of this 8x to the 5th over 3 would be 48x to the 4th thirds.
and then dx out here. And this should all be collectively, okay? And so then this would become what? Oh my, 7 times 40, 280 x to the 4th over 3 negative, and then sine of 8x to the 5th over 3, all of this times dx is what your differential dy is equal to. So just a little algebra there. All right, so now we need to know a little bit about when I create a differential, just how much error do I have? I mean, I'm looking darn good using these linear functions, these linearizations in place of my tangent line. So here's it. Wow, this looks really complex, but it's not bad. Okay, this looks kind of bad, but it's not. So the first thing you need to know is that here's your 2 points that we're focused on, here and here. Okay, here's your 2 points. So we want delta x to be really small. In other words, if your x value here is, say, 1, if you're going to use your linearization and you have an x value of 1, you would only want to use your linearization for like 1.01 or 1.1, maybe 1.2, so your linearization is doing a good job of estimating the value of the actual function. So here we want to know kind of the error in here. So if you're going to get off 1, if you're going to move off of, say, an x value of 1 by a dx amount, which sometimes they refer to as delta x, they're calling dx and delta x kind of equal to each other. Now your vertical lines are interesting. Notice that your f of x is your blue line, and your red line, or almost pink here, this line is your tangent function. Okay, so this is your tangent line to the curve, and they're not calling it L of x anywhere. Okay, so we'll just leave it alone. All right, so we're looking at the vertical part, which is the interesting part here. If you take a look at this amount, which is the difference in the y value between the 2 points, they call this delta f. And so it's the difference in the 2 y values. So in other words, this little logo got in the way. This is the point x of 0, f of x of 0. So this point, if I actually gave it an ordered pair name up here, this would be the point x of 0 plus delta x, or dx, because you're increasing your x value by a small amount, and then f of x of 0 plus dx. So that's that y value. So this huge thing they have written, this is your y value at this point. That's how they get that. So that's your delta f. And then they have a different, then they say this small amount, okay, this small amount, boy, it's hard to get the highlighter in the right place. This little distance here, okay, they refer to as df, okay, they refer to it as df. And it is just, and it is f of x of 0. Okay, that little bit, that little df, and it's kind of hard to see it. But anyway, what we're doing here, and just follow kind of the values in the questions. Sometimes if you over study the diagram, it's a little more confusing than it needs to be. Let's just do this as it says, okay? It says find delta f, noting that it's f of x of 0 plus dx. Okay, they told me that x of 0 is 1. So this is f of 1 plus dx, which is 0.3, minus f of x of 0, which is just f of 1. So this is going to be f of 1.3 minus f of 1. And so when you plug that into the 2x cubed minus 2x, that becomes, on the calculator, I've already done this for sake of time, 1.794 minus 0, so it's a 1.794. Okay, so that delta x difference, you can see in the diagram, that difference in y values when you move 0.3 units away from the original x value where the tangent line is created is 1.794. df here is f prime of x of 0. Okay, so that's the first derivative. Okay, so I need to get the first derivative. I'm not sure where to write this. I guess I'll come over here. Okay. All right, so I need to get the first derivative and then evaluate it at x of 0. So the first derivative of the original function is 6x squared minus 2. So now if I find the first derivative at 1, it becomes 6 times 1 squared minus 2, which is 4. So your first derivative is 4. Now, I'm supposed to evaluate that my df is my differential, like dy, okay, up earlier. And so it's my f prime at 1 times my dx. So it is 4 times my dx of 0.3, so it is 1.2. So don't forget, you're supposed to multiply this times your dx. This is your differential. This is where we're applying that differential information. So now, to find the error approximation in part C, I'm supposed to take the absolute value of my delta f, which is 1.794, and subtract my differential, which is 1.2, and then take the absolute value of it, because there's times where it could be a negative. And so if I do this, what do I get? I get an error of 0.594. That's my error amount. So that tries to explain to you how the further away you get from your original x value where you created your tangent line, quote, your linearization, the further away you get from that x value, and in this case you chose to be 0.3 away when your dx was selected as 0.3, the further away you are, the greater the error will be. And that's how you can calculate the error. So, hope this was helpful. I hope you find differentials to be a lot easier maybe than related rates or some of the word problems that we have come through. And I hope you're ready to prepare for the next test because it's coming up pretty soon.